Start. Good morning. Good morning. Welcome to the beginning of the festivities of the launch of NITheCS. Yeah, I'm very happy that we're all here today, mainly because, as you probably don't know, only yesterday afternoon we got the official permission to be in here. So for the last couple of weeks, we were just squatters, just getting used to the setup. Yeah, but now everything is sorted. Yeah. Now, as you know, we have planned 2 days program. Yeah. This morning, we asked the coordinators or the representatives of the research programs to give us a short overview of what they do or plan to do, because NITheCS is a research institute, so research should be at the core of what we do. Yeah. This afternoon, we will have the stakeholders meeting, yeah, to which all of you are invited, and I hope that some of the DVCs, research of the various institutions forming the NITheCS consortium will join us later this afternoon. In the evening, after the stakeholder forum, we will move to the Drosti Theater, yeah, where the famous director Zurab, where is Zurab? Yeah, organized a theater production around mathematics, AI, science, and so on and so forth. And we will have a small lunch, dinner before the theater starts. Yeah? And later on, we will tell you exactly where to go. It's just all walking distance, so it's not very difficult. And then tomorrow morning, we will have the official launch of NITheCS, also in a building maybe 200 meters from here. We can show you later so that you don't get lost tomorrow morning. In parallel to all of this, our machine learning research program organized a workshop that will start this afternoon after the stakeholders meeting. And Inga reminded me to invite you all, in particular the coordinators of the other research programs, to join them, because as you know, machine learning and AI are everywhere and are slowly taking over the world. So it's really very important that we get an integrated approach to machine learning. Yesterday, we had a talk in the NITheCS colloquium about AGI, yeah? Artificial General Intelligence, and the main idea seems to be that it's closed. So we better get ready to be used to AI that has an intelligence quotient much higher than ours. Yeah? So interesting times ahead. Yeah? Okay, but since we have a very tight schedule, I think we should invite our first presenter, Professor Kang Hui, who will present the Complexity in Biological Systems research program, also confidentially called E5. Yeah? And you can explain what the 5 E's mean. Yeah? We have only one slide change to the program, and that is that Professor Pedro Monteiro, who will speak about the Earth system modeling, climate change modeling, is at another conference and asked if he could give his talk at 12:30. So after the coffee break, we will shuffle around to talks because he's not here. He's physically not here at the moment. So he will give it online. Yeah. Ken, please, over to you.
I'm just gonna... Sorry, I'm just looking for... Where is it? Oh, can you just make it Acrobat or something? Okay, thank you. Morning, everyone, colleagues. So I'm coordinating this focus area, complexity in biological systems. And we have a short name, E5. And 5 E's stand for Earth, environment, economic, ecological, and evolutionary systems. Let me just Mm, um, uh, what is the situation here? Oh, okay. Okay. Where is it?
Yeah, that's all.
This one? No? Okay. So we have this, so the main idea for us as a group is to address this grand challenges at the intersection of biodiversity, climate change, and environmental resilience and sustainable development. And by definition, we are interdisciplinary groups. We are a bunch of mathematicians, physicists, and also computer scientists, also including conservation ecologists and environmental scientists. Our research is very much aligned with the SDGs, so I don't need to argue or specify that too much. And we have a variety of metrics, kind of methods proposed, included in this research, and it's an open-ended, so we very much just start to think about what kind of methods we're going to include in this type of research. We have 5 themes, 5 work packages. So ecological complexity and biodiversity, and it's basically continuing what we already have in a research program. And we also include environmental and climate modeling, and data science and biodiversity in society. And both work package 2 and work package 3 well utilize lots of data scientists techniques and also AIs. And work package 4, animal behavior and movement, and this is a newly identified focus area and work package. And we would like to use reinforcement learning to address this challenge. And last is the coupled human natural systems, which is by a wide group of scientists and aiming to model the social, economic, social ecological systems at the provincial level. So we have this is our team, and for now I'm serving as the coordinator, and Kevin Duffy is the deputy director, deputy coordinator. We also have 5 lead scientists for the 5 work packages. And if you are interested to join us to engage in further dialogue, please approach me or other lead scientists in our group. So next, I just would like to give you a brief of the kind of research we are doing, based on some current and past research that is focused on biodiversity, because biodiversity is a key topic in our research. And for biodiversity change, so we have lots of understanding of how many species are out there, and we also know that biodiversity is changing. So lots of evidence to show that, for instance, the alien species are rising, and also the meta-analysis using global data set that show different taxonomic groups respond to environmental changes in different ways. Some are rise, others are declining. And in the past few years, we have engaged in this advancing biodiversity informatics and ecological modeling with a large group of South African scientists. This is one, basically is a vision statement in 2022. And from this type of collaborations, we managed to have special issues to present different progresses in terms of biodiversity informatics in South Africa. For instance, this is the marine system and the freshwater system. And there are different drivers behind biodiversity change. And for instance, biological invasions, environmental changes, especially the climatic changes. And also, such biodiversity change can have a catastrophic effect. For instance, about 60% of all the flowering plants rely on pollinators for their seed production. And this year, right at the beginning of this NITheCS group, we have this, I would say, kind of like a vision statement to describe the kind of research we would like to do and how we integrate different data sets and evidence. So as an example, we are trying to integrate multiple evidence to study insect biodiversity change. The reason is insects have complex life cycles, and they also have evolutionary strategies, including plasticities, to respond to climate change. Whereas insect communities are embedded in a much larger communities, much larger networks. We have to formulate this insect communities within this much larger systems. And how can we understand the drivers and project the trends of insect changes? So we argue there are 4 types of evidence that we can work on this. The most typical one is time series. Okay, so based on time series, we can forecast, we can estimate the trends. But most of data sets available is at annual frequencies, last for 10 to 20 years. And this is not enough for us to project reliable trends. But time series, nonetheless, is the most important, most direct evidence for us to describe trends. There are also other 3 types of evidence. So we mentioned time series, but you can also describe trends using experiments, spatial comparisons, and expert elicitations. And these evidences will be packaged along 3 dimensions: spatial, temporal, and taxonomic dimensions. And this gives us the biodiversity cubes, so which is a data set packaged along those 3 dimensions to address specific issues. So working with Horizon Europe and GBEF, and we have launched this species occurrence cube at the GBEF, which is the largest biodiversity information facilities. But field experiments are hard, so we can't have too much field experiments. So we rely on mechanistic models as in silico experiments. So this is one example. So we can have such models to describe ecological networks, which is pollination networks, and to work out what are the core and peripheral species and interactions in such systems to better conserve the network function. And in such studies, species traits are very important because we have to infer rates based on species traits or trait matching. And another alternative evidence is spatial comparisons. So we prepare those biodiversity cubes as a side-by-species matrix coupled with additional covariates so that we can eventually explain biodiversity components with coupled environmental predictors. And this, currently, we are pushing the statistic modeling to also include AI and also applications in biodiversity, bioinformatics, ecoinformatics, and geoinformatics. So this is one example. So we have the training data of global forest plots. And from the trained model, we can predict plant and its symbionts in the distribution and its function across the globe. So we have a detailed workflow of how do we kind of incorporate such data. And we have developed and also predicted how biomes, which is the ecoregions, bioregions in South Africa will rise and shift in the future climates. And we're also trying to expand this type of research to cover the entire continent. And this allows us to predict functions, ecosystem services, for instance, wood density and carbon storage globally. So for instance, with biological invasions, with alien species, we can predict invasion probability and eventually leads to policies. And we also show that policies indeed works, although very weakly in mitigating biological invasions. The last evidence is expert elucidations. And this we can see how we can incorporate each expert's opinions and derive population trends. So all of these will be integrated using model-based integration. And this is a co-learning of basically informatics data and also mechanistic generative models. Eventually, we would like to hopefully have a unified theory of biodiversity. And so from data and informatics, and also from mathematics and other generative model, we merged in using statistics and also potentially AI. So this is a very quick glimpse of our group, and you can contact all of us if you would like to engage in collaborations and so on. Yeah, thank you.
That's I would suggest that we defer all the questions to the coffee break and lunch because we have a very, very tight schedule and I don't want to be too aggressive in my policing of the speakers. The next presentation is about our computational and theoretical gravity, astrophysics, and cosmology. Yeah, and the coordinator is Professor Amanda Veldman from UCT, but she's not with us today. And she will be represented by Professor Aram Bisham, who will speak in a moment. Yeah.
edge theoretical models and computational techniques. Now, we have four work packages on transients, gravitational waves, cosmology, and space-time complexity. But, the things are all kind of interrelated with each other, and there's sort of research going on in kind of like all four of them. Okay. Okay, first of all, measuring dark energy with HIRAX. Now, HIRAX, for those of you who don't know, is a radio telescope being made in the Karoo to measure the distribution of neutral hydrogen gas roughly about 6 to 10 gigayears ago. The universe is believed to be about 13.7 gigayears, so you can see that we're going quite far into the past. And this is to measure cosmological parameters. So this needs the development of high-performance computing and machine learning as well in order to analyze the data. And it's used also to measure baryon acoustic oscillation signals to try and constrain dark energy. So work mainly has focused on modeling, simulations, and analysis of the HIRAX instrument. And you can see the kinds of things that are going on and what has been done so far. And simulation tools have involved electromagnetic simulations of various dish and feed systematic effects and processing of these systematics through sort of cosmology simulations. So a lot of simulation and etc. has been going on, and there have been two papers which are at an advanced stage, which hopefully will appear soon. One has been submitted already, which study certain aspects relating to power spectrum constraints. Okay, regarding cosmic cross correlations, now MIRGlass is a survey which is being conducted by this telescope MIRCAT, which is a prototype to the SKA, to create hydrogen-1 21 centimeter intensity maps, which is equivalent to mapping the past 9 billion years of the evolution of the universe. And the idea in this section, cosmic correlations, is to get improved cosmological parameter estimations across multiple cosmic probes. And here you will see the kind of work that is going on. And there are several papers which are in the pipeline, as you can see from this slide. Actually, there's about 4 or 5 papers which are at an advanced stage. Right, then we come to the Atacama Telescope Data Release 6 galaxy clusters. Now, there's this effect called the Sunyaev-Zeldovich effect, which studies distortions of the cosmic microwave background radiation. This is a radiation which emanates from very close to the beginning of the Big Bang of the universe. And the Sunyaev-Zeldovich effect studies the distortions of this through inverse Compton scattering by high-energy electrons in galaxy clusters. And this can be used to detect the disturbance of density in the universe. And as a result, dense clusters of galaxies can be observed. And this can be done across several different redshifts. It's not, it doesn't vary with redshift, so it's very good in that respect. And the method can be used as complementary to measure cosmological parameters through other methods. And this is the largest cluster sample to date. As we said, the mass is limited with no redshift limited, and it's ideal to measure the growth of massive structures over cosmic time. And at present, we do not see any clusters at high redshifts that is sufficiently massive to falsify the well-known and most widely accepted lambda whole dark matter universe. And the work on the analysis of all this data is in progress. And the data and code are actually made public, and there are some of the sites for this. So here's some slides on this. So here you can see the mass against the redshift, and you can see how the number of clusters increases, or I should say decreases with increasing redshift. And there you see the different confidence levels, 95%, 99%, full sky, etc. And let's see if this one works. Yeah. This El Gordo is the most extreme cluster which has been found by the Atacama telescope. Then there is the one by Sikosana et al., which is at a redshift of about 1.5. And then also, this was done with the South African Radio Astronomical Observatory. Right, so let's move on to an investigation of modified gravity models in cosmology. This is one area that I myself am working on. So as we said, there is a standard lambda CDM model, which is used to explain dark energy and the current expansion of the universe. So we have found several models, and this gives us some indication of the solution to the Hubble tension problem. And another problem that has emerged is that the current equation of state is not constant, but could vary. And then there's this preprint here, which involves Roy Martins from the, who is one of the members of our group. Right, I'll just go quickly to pulsars, fast radio bursts, and machine learning. There's machine learning for you. Okay, and then there's a related gamma ray bursts as well. So these things could be used as standard candles to investigate, again, the Hubble tension and also other cosmological parameters. And this is these are some of the things that are going on: code speed up, population studies, topological analysis of large-scale structure, and the progress in this direction. And as we said, gamma ray bursts can be used as cosmic probes. And here's some research questions which are being addressed. There are some postdocs also involved in this, and there are some publications which have taken place. Right, so coming to gravitational waves. Okay, these are probably the sort of smallest disturbances which have been predicted, and the first observational confirmation came in 2017 in looking at the merger of two neutron stars. Okay, so this gives an idea of some of the work that's going on, comparison with numerical relativity, quasi-normal modes, pulsar timing data from Meerkat. Okay, so we are planning also a workshop sometime later this year to try and have sort of more interaction, cooperation with the various groups, because we've got a large number here, around 38 people. Thank you very much.
Yeah, thank you very much.
Okay.
Nice presentation. Let's move to the next presentation about the research program on decoding the universe. So we go from the big to the small, the presenter will be Professor Will Horowitz from UCT, who is not the coordinator. Yeah,
Correct.
but you can maybe share that information, please.
Thank you very much. They got a few little delay. Since you know. Great. Okay, so it doesn't like that one's the same one. This one's all right. Yeah, see, it's cool. Very good, thank you.
Thanks.
Good. I was asked to wait a second. Okay, great. So thank you all for coming. I really appreciate you taking the time, and for those from out of town, especially for making the trip. As mentioned, this is the Decoding the Universe working group, and we're redefining the foundations of physics and transforming the landscape of formal theory in South Africa. This was prepared by our fearless leader, Vishnu at WITS, and presented by me, who's cut off at the bottom. There we go. Good. So for some context, we're looking at Bronstein's cube. So these are the three directions that we can think of for modern physics. We can think about quantum mechanics, where h bar is large or is important. We can think about special relativity, where the speed of light is not huge. And we can think about the force of gravity, the gravitational constant is large. And the idea is that this is our usual classical mechanics that we know and love. And we would like to understand what happens in the quantum world, in the special relativistic world, in the gravitational world, but going out on multiple of these axes simultaneously, which is very hard. So if we want to go to quantum mechanics and special relativity, that for instance is quantum field theory. We want to do gravity and quantum mechanics, but not special relativity. This is Newtonian quantum gravity. Gravity and special relativity is general relativity, classical general relativity. And the combination of all three of these is quantum gravity, a quantum theory of gravity. And this is a big question mark, which we don't know currently. So this would be the unification of all of the greatest ideas of the last centuries of physics, with the unification we'd like to understand. Good. Apologies for the delay. So the fundamental questions that we would like to address: why is the world the way that it is? Could the world have been any other way? What is the fundamental explanation of space, time, and matter? Where do these things come from? What are the organizing principles of quantum field theory and quantum gravity? And can we explain the unreasonable effectiveness of mathematics in describing the natural world? These are immodest, but this is what we would like to do. There's no reason to do easy things. Okay, so gravity, we can understand gravity in the classical general relativistic sense from the Einstein equations. And then there's a standard model, so the quantum field theory of our universe as we understand it for all forces other than gravity. And what we would like to do, amongst other things, but one of the main focuses of the group is to try to merge these two ideas simultaneously. And that is a very, very difficult problem. Why is that a difficult problem? Because a naive attempt to treat gravity as a quantum field theory fails, that there are infinities that we cannot deal with. And perhaps taking a note from the development of quantum field theory and many, many Nobel Prizes, and for example, the dealings of the weak nuclear force, the idea is to smear these interactions to make them finite. And that leads to string theory. So string theory is what we think of, well, string theory is a consistent theory, quantum theory of gravity. There are some difficulties. So it's finite. We're very, very happy with that. But one is led inevitably to the notion that space-time is rather than four-dimensional that we know and love, but rather 10-dimensional or more. That's a certain conceptual difficulty. And further, one needs to test these theories. That's physics, that is science. We would like to do science, and that's hard. So as commented, string theory is a web of interconnected theories in 10 or more dimensions. The idea being that these extra dimensions are tiny, and then we can therefore, through the compactification of these extra dimensions, explain physics that we see in the world around us. I think many of you are well aware of some of the difficulties that people have found in trying to make quantitative predictions from a quantum theory of gravity, that the natural scale that one is working on is the Planck scale, which is way beyond the measurement capabilities of us today. Nevertheless, we're endeavoring. But also there are some amazing progress has been made in the notion of holography. So this is the idea that one is able to map problems that are difficult in four-dimensional space-time, like we live in and know and love today, into a higher dimensional, say 5 or more dimensional volume, and vice versa. And so one can gain insight into the physics of four-dimensional flat space-time, for example, quantum chromodynamics at strong coupling, by mapping to another theory, which would be the quantum theory of gravity, in a larger space-time, in say 5 dimensions, where the difficult problem in 4 dimensions becomes an easy problem in 5 dimensions. And this problem also works vice versa, that difficult problems in 5-dimensional gravity might be easy in 4-dimensional flat space-time. So this is the famous Maldacena conjecture, this duality between type 2B string theory on a certain manifold in 10 dimensions and a supersymmetric theory, quantum field theory in 4 dimensions, technical details. So we have 10 work packages. There's been a lot of progress in all of these work packages. Because of the limited time that we have, we're going to focus on about half of these as we go forward. We're splitting these up into the quantum gravity in the red and quantum field theory in the blue. My particular area is 10, and that was neglected. I don't know why. Okay, thank you. Very good. But you can talk to me later about all the amazing things that our group has done. All right. How am I doing on time?
6 minutes.
6 minutes. Okay. So quantum gravity in the lab. I'll give you some of the big pictures, and you can refer to the details of what has been happened in the past by looking at the slides online. So the big picture in quantum gravity in the lab, as I mentioned, the usual notion of trying to test quantum gravity by looking out in the universe has so far not yielded anything that has been a quantitative test of the ideas of quantum gravity. So we would like to try to perhaps go into a tabletop experiment. So can we transition, or can we extract ideas from quantum gravity and quantum information into tabletop experiments that can then probe how space-time and information are connected? Again, this is the idea of the emergence of space-time from quantum gravity. Holographic complexity, our big picture, we'd like to use the tools from quantum computing For example, how many steps does it take to build a quantum state? To give a clear quantitative handle on how space-time emerges from quantum states. Again, these are the big pictures we would like to try to address in our work packages. I would like to highlight, especially very impressively, last year there were 5 peer-reviewed JHEP papers coming out of this particular area. JHEP is one of the most important and prestigious peer-reviewed journals in our field. Large and gauge theories. The big pictures we would like to unite rigorous theory. So for example, matrix models, a particular type of quantum field theory, and holographic dualities, like I mentioned, this Maldacena conjecture, using high performance simulations and to understand strongly interacting quantum systems, which would advance both QCD physics and our understanding of quantum space-time. So this is where one is trying to put all of physics onto a computer and trying to discretize. There are many challenges involved with that. But it's a very important, very large area of physics that have many people working on it, and we're making important contributions. And what's actually particularly interesting is that the focus here is on doing these lattice calculations in supersymmetry, which is very interesting because then you can quantitatively test these dualities in a system where you can change the scale of the coupling, the strength of the coupling, and precisely probe these dualities. And this is really, really interesting cutting edge work. Exact results in quantum field theory. So the big picture, we'd like to develop exact tools, supersymmetry, index theorems, integrability to solve quantum field theories and extend them from ideal test beds to more realistic models, cross-checked against their gravity duals. So this is extraordinarily formal work, very interesting work. And the idea is to take things from the top down, to go from these very formal ideas that are very interesting in their very idealized settings, and then try to make contact with the real world. Because again, we're not mathematicians, we're physicists. No disrespect to mathematicians. Okay, towards the real world. So use machine learning to uncover and organize mathematical structures arising in string theory, connect string geometry to phenomenology, aiming at realistic string models of the standard model, and early universe cosmology. As I mentioned, the idea of string theory is that we have 10 dimensions, and we need to turn those 10 dimensions down to 4, and there are ordered 10 to the 500 different ways to do that. And so you need new interesting ideas in order to probe that enormous phase space of universes, potential universes that could come from string theory. So this is known as the swampland, and we're trying to carve out some region of clean water in the swamp. There have been a number of workshops, many of these in Johannesburg, focused or centered at the Mandelstam School, and schools on string theory, where there are some nice international connections. And then there was the very nice workshop that was here in Stellenbosch recently. Thank you very much for hosting us. That was really, really quite nice. In the future, more Joburg schools on string theory and Mandelstam schools. And then very exciting for us in the last work package is an inaugural heavy ion workshop at the University of Cape Town, which is led by that work package's leader, Isabel Colby. And this is really nice, I would say, to highlight this last one, which is in my area, so I will take a little bit of freedom to mention this. That really what this is indicating is a new critical mass, that there's now a critical mass of people in the country working on the heavy ion physics, and it's being supported by NITheCS, which is very, very helpful. So thank you for that. All right, to wrap things up, our focus areas is ambitious goals. We want to understand the universe at its most basic level and make that connection to the world that we see around us. Much of the work is formal, but it does make contact with the real world in terms of experimental measurements in particle and nuclear physics, observations in cosmology, model building, simulating physics of strongly coupled systems, and developing quantum gravity in the lab. Research is topical, contributions are valued by the international community, many publications, lots of citations, lots of excitement, workshops where we have international connections, collaborators coming here and being excited to work with us on these topics. And we're really fortunate to be working at a time when these foundational questions about space-time and matter can be definitively answered, where we have multi-billion, multi-tens of billion rand experiments and collaborators who are all working on these ideas and want to work with us, and we're making real contributions in these areas. Thank you very much for your time and attention.
No, thank you very much. Well, you didn't even need a warning to finish on time. Thank you very much. That was just perfect. Okay, so the next presentation is by Professor Özlem Tristan Bishop from Rhodes University, who is the coordinator of the research program on Afrocentric solution for disease control and healthcare. So, Özlem, over to you. Okay, we are getting better at the transition, so that's very positive.
Yeah. Okay, so
Yes.
Presentation, is that the one?
That's right. Okay, perfect. Okay, good morning, everybody. My name is Özlem Tristan Bishop from Rhodes University, and the short title of our focus area is Data-Driven African Healthcare Solutions. I'm unable to go to next one. None of the arrows working. Okay, I'll go from here. Yeah, okay, cool. So currently we have 15 active members. They are from all around South Africa. We have a member from University of Limpopo, 2 from Northwest University, 1 from UWC, 1 from UCT, a number of them from Stellenbosch, and 3 from Rhodes University, and 1 from University of Zululand. Initially we were 20 people, but 5 of them unfortunately dropped out, especially after seeing the budget. It tells us something, I assume. Okay, out of these 15 members, 11 of them are senior and 4 of them junior academics, and we try to attract more junior academics actually. We have diverse backgrounds. Some of us are coming from bioinformatics, the others from population genomics, here 1 physics, astrophysics, and computer science, and computational chemistry. So really we have a pretty much very diverse background. So how we go with program coordination? This year I'm coordinating it with Prof. Marlo Möller and Caroline Rose, Dr. Rose. We try to divide the job in a way that there are 2 senior and 1 junior academics to push the junior academics to get more experience in this kind of things, and starting from next year, Yapi, Martin, and Fortunate will take over this position. Okay, initially we had lots of research teams, and one of the things that we did to collapse them under 5 teams, which is more manageable, especially with the number of people that we have. And these teams are coordinated by one or more people. And again, we try to give these jobs to the junior or middle career people. These teams are basically drug discovery for communicable and non-communicable diseases. We have rare diseases, we have wellness and technology, and we have pharmacogenomics, and the last team which basically collaborates with the other ones is the tool development and computation modeling. So what we have is these coordinators coordinate research activities within the teams and report back in our monthly meetings. Okay, so each of the team has key members from focus area, and of course we have national and international other collaborators working with us, and we try to bring more people currently to each of these teams. We have a number of short-term and long-term objectives, and one of the main things that we want to do is to establish new interdisciplinary collaborative projects, and I think we are getting there, and next week we will have a focus area workshop which will help us to settle down in some of the potential projects. We also continue with the existing projects. We would like to really collaborate with early career researchers and put them in contact with the established national and international scientists, and recruit postgraduate students and postdoc fellows via NITheCS funding. I think we are pretty successful on that. For instance, from Rhodes University, there are over 10 MSc and roughly 5 PhD applications for next year. I don't think that we all will get it, but this shows actually the demand that we have for the bursaries. And disseminate knowledge by developing tools, web servers, and databases. We have already a number of them from our previous studies, but I'm not gonna summarize what we had individually, but try to give some examples from collaborative work that we have. Long-term scientific objectives, because we are working in health-related projects and drug discovery projects, we really would like to see the transition from research outputs to tangible clinical impacts, and we would like to do that by actually collaborating with industry and biotech partners. Some of us already have industry partners like Novartis, GSK, but we would like to take this further. Sustainable research, capacity development. I think we are already doing this. These 4 junior academics that we have were actually our PhD or MSc students, and they are now in the system. And we would like to be recognized as international leaders, which is also, I think, happening. We are part of some Aura Guild course, research course, such as GHA, which is Genomic Health for Africa, and AI1. Okay, I just would like to quickly go through each of these themes. The first one is drug discovery for communicable and non-communicable diseases. We know that there are lots of diseases in Africa and drug development is very limited for these. But if there's any drug for these diseases, we unfortunately face to drug resistance. And this circle is not there. When there's drug resistance, the replacement of these drugs with the new ones is not as fast as getting the drug resistance. So this circle is broken. So the aim of this team is basically to obviously identify compounds, can be druggable compounds, but while doing that, we also would like to keep in mind that we have drug resistance and we want to design things to escape from drug resistance issues. So our objectives here are surely to identify hit compounds and hit to lead compounds, but while doing that, we want to understand, do some mechanistic studies like understanding drug resistance and predict the evolutionary mutations, feature mutations, which is very challenging topic, I have to say, because viruses and pathogens have their own mind and they always find a way to escape from drug pressure. And the other important thing is to understand human pathogen interactions, and African human genome is very unique, and that's why pathogens have different mechanisms and the humans are differently affected by pathogens. So pathogen virulence is slightly different for African people. So we also would like to, of course, develop tools and pipelines, and this is basically collaboration with team 5. This team is actually adopts One Health framework by looking at humans and pathogens. We do not look at, we don't have projects in animals, plants, and crops, but the methodologies and approaches that we develop is actually applicable. So in that respect, we hope that in future we might be able to collaborate with this domain of research. This is just one example where we 3 NITheCS associates collaborated with the 3 PhD students here, and they all have now NITheCS PhD bursaries. What we did here by using structural bioinformatics, computational chemistry, graph theory, and machine learning, we try to predict the feature mutations in SARS-CoV-2 main protease. I'm not going to go to details, but what we did, we used graph theory as a prediction. These are the residues that are not mutated in the protein, and when we applied a combined of this information and applied machine learning, as you can see, the prediction improved. And this year we published this article showing that actually what our machine learning model can be applicable to certain proteins. So this is really important in a way that if we can find a good model, we can apply to any virus in future, which is important for pandemic preparedness. Okay, so team 2 is about rare diseases, individually uncommon, but collectively impacting millions. They are not really rare. And this team is led by a clinician, a doctor, and our aim is here actually is to bring geneticists, molecular biologists, clinicians together with the computer scientists. I think there is lots of potential here. We have different research teams. While doing that, we would like to build the capacity where clinicians, clinician scientists would know more about computational analysis and also get the data collection better here. So this team is about more mechanisms of why we have rare diseases. But if we know these things, of course, it would also help us to collaborate with Team One for drug discovery purposes. And in all cases, we would like to create tools, especially for this one. There's hardly anything to predict how certain variants can cause diseases. Wellness and technology, this is often forgotten among all these communicable and non-communicable diseases. So here we would like to use technology, bring the technology-based interventions with traditional treatment to help give mental health support. Apparently, roughly 27% of South Africans are affected with depression, according to Employee Association, Assistance Professionals Association. Okay, team 4 is about pharmacogenomics. We know that African genome is different than the rest of the world, but the drugs are designed for mainly for others, Europeans and Americans, so that causes lots of drug toxicity issues, and this team is working on that. We have a number of articles. I didn't list them, but and the Stellenbosch team is mainly very active on pharmacogenomics and personalized medicine aspect, and the aim is to understand how specific African human genome variations can cause these diseases. So of course, all of them we will come together at the end as Team 5 to tool development and computational modeling. So expected outputs, well, I mean, we have already a number of things. We have already pipelines, web servers from our previous studies. Now we want to further develop this for each team: drug discovery, rare diseases, mental health, and pharmacogenomics. We want to graduate MSCs. We have been doing this already. Strengthen collaboration. We have collaborations, international and national. One of the most recent thing perhaps that I can report, we are writing a course application in rare diseases with University of Tübingen and University of Bern. And I think this is all said, and Francesco is looking at me stressed, so thank you.
Thank you. Yeah, thank you very much for another great presentation. And the next speaker is already running to the podium. Regina, welcome. So the next speaker is Dr. Regina Merpanga, and she will speak about the computational modeling of functional materials research program. Thank you very much. Yeah. Great. That's the appetizer. Yeah. Yeah, but 10 minutes times 10 is a long time. We'll do it better next time. No, that's the theory. Yeah, you like it. Okay, okay, nice. Thank you. Yeah, yeah. It was
What was it?
mechanical work. That's why everybody hates me in physics.
Good morning, everybody. So I will be presenting our focus area titled Computational Modeling of Functional Materials for Driving Sustainable Innovation. So this is one of the focus area. It has been there before, but it comprised of fewer members. So it is only in this cycle that we've got an increased number of members. Hence, I may not be able to show some of the previous results that were achieved. I'll also highlight what are the new things that we will be doing in this cycle of funding from NITheCS. And I am the coordinator of the program. I will introduce other members as I proceed with the presentation. And I liked this quotation, which I think it came from NITheCS, but due to limited time, I'll move straight to the presentation of our focus area, which, as I said, it is titled Computational Modeling of Functional Materials for Driving Sustainable Innovation. And our goal is we support three of the Sustainable Development Goals, which is goal number 3, 7, and which are goals number 3, 7, and 13 on health, energy, and climate change. So the focus area is mainly about the development of materials. So we intend to leverage the advanced computational methods that have been developed over the years with a combination of machine learning techniques to accelerate the discovery and design of functional materials. And as I mentioned, to support the SDG goals number 3, 7, and 13. So in short, we combine both the physics-based models and machine learning models to develop new materials which can be used for different applications. And we had identified our scientific objectives as follows. We've got 6 of those. The first one is about achieving fundamental understanding of energy interconversions, where we'll explore and establish a deeper understanding of the different properties that are related to energy conversion and storage. And I also need to highlight at this stage that our focus area touches from the fundamental up to the high end, where we envisage that some of the technology or the materials that would have developed together with their technologies would be commercialized. And our second objective is to develop new organic polymers for energy production and radiation shielding coatings specifically for space applications. And the third objective is to determine the role of intermolecular interactions in energy processes. So the first and the third objectives are closely related, but they follow different approaches, as I will explain later. And our fourth objective is to develop polymers and bio-inspired materials. This is the goal that is meant to support the health component of the focus of the SDGs, where we are looking at investigating the intra and intermolecular structure function relationships of soft materials. And in this under this, we'll look at properties such as molecular aggregation, the environmental tuning
with specific aims to understand the molecular principle underlying the emergence of complexity, particularly of materials in health applications. And our fourth objective is on the development of battery and catalytic materials for hydrogen energy production and storage. And this is driven mainly by the global drive on the hydrogen economy. So we intend to develop materials for such applications. And lastly, or the last objectives on the development of computational methods and algorithms for discovering materials. So this is an objective that is specific for application of AI and machine learning. And with this particular objective, we envisage that we will develop a tool or a software that can be used to design or to come up with new materials. And it is intended to help the experimentalist to quickly go to the lab and synthesize such materials. And in terms of the research themes, these are also our work packages. And we identified 5 work packages, the first one being the fundamental principle of functional materials. And this responds to objectives 1 and 3. And I would like to refer to the specific objective of this work package. So the first objective is to analyze atomic and molecular structure to unravel structure-property relationships. We'll also predict materials functionality in process conditions using phase diagrams. Then we'll also optimize and propose rational design principle for incorporation in a materials application. So these are the objectives for the first work package, which is focused more on the fundamentals. Then the second work package, or the second theme, is on machine learning for designing novel functional materials which respond to objectives 5 and 6. And as I said, what we intend to do in this objective is to take the data that has been generated from either experimental or traditional computations and apply machine learning to those to either discover or predict the properties of these materials. And in addition to that, we will develop a specific code that can be used or a protocol that can be used to design new materials. And the third work package is on functional materials for energy applications. So this also, it combines the traditional physics-based models together with the machine learning to specifically design materials for energy applications. So the previous objective, it might be for the previous work package may consider other applications, but the third one is specific for energy applications. Then the fourth work package is on functional materials for space application. And in this case, what we intend to do is to use multi-scale, multi-phenomenal methods to unravel materials properties, particularly for space environment or space applications. So we will combine the quantum mechanical and molecular mechanics methods to design materials. And also in terms of the type of materials, we will focus on the nanomaterials, unlike in other work packages. And lastly, the work package on functional soft materials. So this work package is about designing bio-inspired and polymer materials, which would be used in health-related issues as well as in energy. And moving forward, we also present some of the contributions which we believe that the focus area will make an impact and is relevant to our societal needs. We've identified our scientific impact as well as societal impact. So we will build expertise in advanced computational materials modeling, which uses both physics-based models as well as machine learning models. And also we intend that we envisage that through this program, we will develop leadership in terms of novel novel energy and space materials and systems. And also we will come up with new innovations, particularly in terms of development of functional materials, and also through the machine learning code development and tools. We intend that we'll develop new algorithms and new computational methods, particularly from the combination of different methods across the scale. And in terms of societal impact, I think the project will contribute to energy independence and security, which is one of the critical issue that we are dealing with in the country. So we believe that the technology that will develop from the focus area will contribute to that, as well as to the environmental sustainability, skills development and transformation. And also we envisage that some of the technologies that we develop in the long run, they will contribute to job creation, which ultimately impact the economic growth, particularly if those technologies are to be commercialized, and also the workforce that would have trained into this, they will be able to contribute to the economic growth of the country. So moving to the framework that we intend to follow, as I mentioned, we are going to combine both physics-based and machine learning. So we have been using the physics-based models. So what we intend to do now is to combine the different methods to come up with new materials, and just to simplify the different models. So traditionally would have a program which we feed into the computer to get an output, and with regard to machine learning is vice versa. We take the data that has been generated, put that data into the program, into a computer, and come up with a program. So we are going to combine the two approaches. And I've been talking about materials in general, just materials for energy, without specifically specify which materials. So the material research area is quite broad, and it was important for us to limit ourselves to specific materials. So as I said, in terms of application, we identified 3 key areas, which is energy, environment, and health. And under those, we are still going to go down to look at specific materials, because the landscape is quite broad. So this is a summary of the different areas that are found that can be explored, but for the sake of the program, we'll limit our applications to those 3 and to specific types of materials. And in terms of the outputs, these are the outputs that we envisage will achieve through this program. So I'll focus more on the outputs for this financial year, which we already had 2 mini schools. The other one took place in August, and the other one will be taking place this month in September. And we also had webinars, and some of the work has been presented at conferences. And also to highlight that we had an outreach activity during the Women's Month in South Africa, where we had a high tea for girls in physics at the Northwest University. And in terms of the publications, we are still working on those, and we are hoping to deliver something by the end of the year. And in terms of participations, these are the participating universities. So we've got a total of 9 principal members, which have sub-members in their groups, which I did not include in my presentation. And out of those 9 members, 3 of those are females and 6 of them are males. So this is the representation in terms of the universities that are participating in the program. And that's the end of my presentation. Thank you.
Yeah, thank you very much. It was very nice presentation. Thank you very much. I think we should thank all the speakers of the first session. They took the time constraints very seriously. So thank you very much. Thank you. And according to plan, there should be coffee and some snacks waiting for you outside, and we meet again in 15 minutes here. Yeah. And maybe the speakers of the second session can liaise with our two technical experts at the back to make sure that everything goes smooth. Thank you.
Wow, impressive.
Yeah, you write up nicely. of the research focus areas. The next one is about driving innovation in finance for sustainable growth. And Herman Donfak will replace Professor Mesias Alfeos, who is the coordinator. But I think we hear that his family is getting bigger one of these days, so he couldn't be here. No?
Sure.
Herman, please, over to you.
Thank you very much. Like Bob said, many of the slides, most of the slides were prepared by NITheCS, and I'm going to try and guide you through what the quantitative finance focus group is planning to do, or some of the things that they've done already. So in the world where we are facing this very volatile market and energy transition, we have to also think about how do we design instruments that are adapted to that. And this also was kind of already generated by all the chaos of the greatest financial crisis. We saw basis credit explode, and it will quickly become obvious that we need to think differently about how we talk about issues like counterparty credit risk and centralize some of the derivative instruments. The model risk became very important, especially because model risks were one of the reasons models were blamed for why the crisis occurred. So in the South African context, we, following the rest of the world and for other reasons, we decided to transition to the Zaromia as a benchmark rate. And we also, as we all know, face this electricity supply chain, the shocks. And due to some other factors, we see swing between cash flows in and out of the country. So in that context, what we're really trying to do is to present a practical research-led agenda, linking sustainability, sustainable growth, market stability, and energy resilience. So our objectives are to frame it as a leading hub of advancing quantitative finance for sustainable and inclusive development in an emerging market. So this is centered around these three objectives. The first being a building model that integrates ESG and energy dynamic into the risk, the pricing, and the strategic allocation of assets. So we also know that we need to strengthen market infrastructure. And this is done by, already started with doing the inclusion of this change in the benchmark rate and monitoring our liquidity gauge and thinking a bit more scientifically about the policy tools. And so what we hope is to also deliver industry-ready methods that are that regulator will be happy, and in the same times not leaving some of our historically disadvantaged institutions behind. So that's what we really would like to achieve. So on the first pillar, so I'm going to have to talk about three of them. This is where which is mostly about integrating ESG factor into the pricing and risk budgeting and strategic allocation. The idea here is to actually, take seriously those derivative and financial instruments that have those clauses, those ESG clauses and all that, and price that in and see how it gets. And we also interested in how or when a system choose not to really follow the transition, the energy transition, what could happen. And so that's where the stress testing of a portfolio comes into effect. And around that, we obviously have to work on econometric models that that will kind of be the guides on what to include or what kind of factors are relevant to our field. And so as a whole, we will hope to generate an actionable framework for asset managers and policymakers. So in the second leg, so we have working with stochastic model for energy prices, like also energy loads. I mean, how does it change in a different city or town or country? And also a model that's a renewable penetration. And we include in this block the study of our structural risk, right? And saying how is our energy supply organized, the transmission, what are the things that can go wrong, and what are some of the vulnerability by creating models that are designed to study this kind of system. So behind that, we obviously will have to work on electricity-linked derivatives, work on a scenario engine for policy design. And in this, the deliverable will be some sort of a pricing theory, forecasting tool, and some sort of a design recommendation, market design recommendation, sorry. The third pillar is how to do with the Zaronia. So the idea here is to take into account this specific context of Zaronia and come up with dynamics interest rate models that as a match that calibrate those models and take into account those component like a rollover risk. And so we also want to quantify what will happen when, I mean, it's very common when you adopt rates, there's going to be some deviations, and I need to understand how it works and what are we going to do about that. And so we also have to take into account some of the, I mean, how it integrates now with some of the challenges that you can have in the market. For instance, is Zaronia is liquid as we want it to be, right? And what are the implications on the pricing of the derivatives? So and we know that having a credible benchmark and a robust hedging will really help make our market more attractable. So across that, I think I'm going too fast. Oh yeah, so one of the, let me just check. No, I think I'm going wrong side. Apologies for this. Oops. You might, I'm gonna go manual, sorry. So yeah, I talked about this. So one of the, I mean, we also interested in the conversation around machine learning, and the idea in this project was to, and it's still a continuing project, is to use a variational autoencoder to complete volatility surface. So we work in a market that can be illiquid. And so this, taking advantage of generative model to complete surface, it become an attractive idea, and it could be useful for stress testing and also be used for tooling and risk control. So on the policy side, we kind of, like I mentioned earlier, we have this issue of cash flow control, and what we really want to understand what are the best model to study this kind of risk. Particularly, you have what the central bank would like to look at interest rate corridor, what are the optimal ones, and what can we do, for instance, if people want to feel our market or are just trying to manipulate it. So what are the tools that we can put in place? And that is what we really need to support our macro-prudential playbook. So we're actually very pleased to talk about this topic. It's the brainchild of NITheCS, which is how to do with creating this wine index. And the nice thing about this is that it's really about our wine. And I think the context is cannot be more stressed given the tariffs. So we so we can be proud that we have this index, and it has actually been tested, and some of the results show that it could help strengthen some portfolio. So we also really happy to have this project. It's basically what this leg does. It's interact with industry, where industry suggests problems that we can then put out there to our community, so they can work. The scientists can work on in collaboration of the industry person who suggested the topic. And through that, we have really the best of both worlds. The industry gets to give us real problems. Then the students and the researcher also get that contact with the real world, which is sometimes easy to miss when you are in your research lab. And all of this, we know, is going to be really nice to expose our students to practical problem and get them ready on day one to contribute to their job or the job's place. So our impact really, if you think about on the economic and policy side, is to contribute to a stable benchmark, better aging and efficient energy, improve macro-prudential readiness, especially in regard to capital flow. On the scientific and societal side, of course, it's going to be lead to more publications and software policy and contribute to policy brief. And lastly, but improve the pool of skills in this area of quantitative finance. So what we really can summarize in these KPIs is the accuracy of forecasting tool, adoption of regulator, industry, and training outcome for successful PhDs completion. The roadmap looks like follow. So of course, some of these projects have started, and we just have this 2-year plan, and we will evaluate it, and hopefully we meet all of this target. So our call to action really is for banks, regulator, and state-owned enterprise to help us co-develop this pilot models. And it's very important to have them, because they can also help us with sponsor the data. They can help us to increase our computational power. This is really needed. And also adopt the tools that are designed, right? So we can have a feedback that says, okay, how's that going? And especially in the for project that they actually suggest we work on. So our call of action is to build a resilient, inclusive market for a just energy transition. I'm going to stop here. Thank you.
Very important presentation. Thank you. I think I would like to ask Professor Inga Fabrice Rotelli now to present the next research focus area, and we will move Professor Pedro Montero last, because he will join us online, and so we don't, in case it doesn't work, we will do a short process. Yeah, Inga, please.
Okay.
Thank you very much. That was really nice. Thank you.
Thanks, Jeff. Yeah. This is just the general function for NITheCS for this year.
Yeah, I think so. It's more than enough. No, but next year we will do it again without all this festivities, so we have more time.
Next, should we even start thinking about?
Yeah. No. Yeah.
I thought, what was his name? A man, a new person at once, and the football.
Yeah.
Don't think that he understands. He said, send the invoice and I will pay.
Yeah, no, but he will be here tomorrow. We can speak to him tomorrow.
Is possible, right?
Yeah.
Yeah, we need to decide what he has not to do.
I know. Okay, that's good.
I mean, so
Why?
he doesn't know. I mean, it's so clear.
I don't know. I don't know. But he should be here tomorrow. He started very recently. Yes. He started very recently to be the head of knowledge. It was admin dean. I know, but some people don't learn fast.
And sending noise and get to possible.
Let's see.
I wouldn't do
He
it.
needs to send it to me. Yeah.
Afternoon, everybody. So I'm Inga from the University of Pretoria Department of Statistics. And our group is called Elevating Data Analytics and Machine Learning in South Africa. Part of it is about advancing capacity in these fields in South Africa. So I've got a nice team. Got Tian and Marley and Sunay, Priyanka, myself, Justin, and Stefan. Those are the main PIs, but you'll see just now got quite a lot of collaborators. Okay, it does cut off a little bit, but right. So we're focusing on. So we're essentially a statistics, machine learning, data science, AI group. Two of the pillars, two of the bits in the circle of the eight bits in the NITheCS circle that we've merged together. So we've got three sort of what we call pillars of impact. The one is theoretical statistics and machine learning, but not to only be theoretical. We've got two other pillars. One is sustainability support for statistics and machine learning academic departments in the country, staff and postgrads. And then the third is community service and collaboration. And I think not one of you have done a presentation so far. We haven't mentioned machine learning, data science, or AI. So I think we are at the center of everything in a sense. I do have AI in it. Francesca, look at that. So that's our third pillar, is very much about collaboration. And NITheCS is that's one of the important things about NITheCS. So that is one of our pillars. So it's our theory, but it's our community and it's sustainability of our fields. So just some screenshots of that nice document we wrote. So these are our teams. Marley leads this team. She's from Northwest University, so you can see a variety of institutions there, as well as some international. Tian is leading this team, obviously some name overlaps, but also a variety of institutions. That team I lead there with Justin. So Justin is the HOD of the stats department here at Stellenbosch. And we've got quite a few team members there. That group, I'll talk a little bit more about just now, but is very much actually across the whole country in all of the universities already. But the main core team members are those institutions there. So you'll see here I've got our Stats NITheCS members, and they're across all the stats departments already in the country. Priyanka then leads a theoretical statistics group here at Stellenbosch University, but also some international collaborators. And Sunay, who's at the back there with the cute little doggy, is from Muvisu, yeah, also at Stellenbosch University with a number of collaborators. So in terms of theoretical advancement, we are working from our work packages. These are the main items there. So knowledge discovery in complex sequential data, generalization in deep learning. So there's our AI again. And then we've got multi-dimensional visualization and analyzing hidden patterns in complex data on different manifolds. So the first two are computer science driven, and the second two are from the stats groups. But as we all know, computer science is basically everywhere. AI is basically everywhere. Then the second pillar is our academic sustainability. Sorry for the cutoff. But so the stats departments in South Africa are severely constrained in terms of capacity, every single stats department. So my department is UP, is the biggest stats department in the country, and we are also constrained. Obviously, it's relative to the size of your institutions, but we do not have many senior professors. All of the senior professors, let's say 95% of them are basically already retired and moving out. I'm one of the oldest people in my department. And I'm not very old, but I'm also not very young. So that is a big problem. And this is what we see across all our departments. So we're getting a lot of young staff coming in, but because we have no capacity, people are worked to the bone. We have huge classes. I think in every university in our country, we teach every single student in the university. Everyone has to do a stats course. So we're severely constrained, and we don't have this mentorship of senior profs. So our group, Stats NITheCS, was set up already in 2020 to develop a horizontal mentorship platform. So we help each other. I don't know, but you don't know, but maybe we can figure out together. So we have a number of initiatives which you can see on our website. So this is what this group does. We effectively focused initially on post-grad supervision, training of that. How do you learn how to supervise a postgrad student? Bearing in mind we have no senior mentors in our field. And that sort of filters into the rest of your research. If you can supervise a PhD student to success within minimum time and grow them into an academic who's solving a lot within the field. We already have almost every HTI in our group. So they're not listed as PIs there, but they're in our group. As in many fields, the HTIs are very small, and a lot of our HTI universities don't even have a stats department. They're sort of blended with something else. So it's there's a lot of issues there. Once again, something about AI. So this research group, which is specifically my research group, is actually working on AI in research. There's a lot of work being done on AI in teaching, but we're looking about AI in research and specifically in supervision. How do I, as a supervisor, know that my student has handed me a document that they asked ChatGPT to write? Okay, we all need to learn these things. So we're doing a lot of that. How do we assess now that they can ask ChatGPT to write their whole thesis? What should we be doing? All those sort of things. Okay, and then the third one really is about how do we use statistics and machine learning in all the other fields? Okay, so as a basic science, statistics, machine learning, computer science, we obviously focus on our own field, but one of the things we always end up doing is contributing in other people's field in an applied mechanism, right? And both of those pillars are really important, not either or. We have to be doing our core research, but we also need to be doing research where we work with others and contribute to science in general. So our third pillar is really this. So it's about facilitating collaboration and support across all the fields in the NITheCS colorful circle. Our societal and scientific impact is really about pockets of excellence for individuals for the future. We are theoretical advancement, so the core of our field, statistics and computer science. You saw in our work packages, the computer science development is very much about explainability in data science and AI, which is huge and really, really important. We want to produce graduates with who have been holistically trained. So they're not just someone with a degree, they can critically think, they can go into industry, or they can stay in academia, right? That's really important for us. You've got to have both paths open for a master's or a PhD graduate. Our group is obviously also doing research in education statistics. How do we, so not only school, but university, how do we as university lecturers, how should we teach statistics? How should we supervise statistics? We have a few publications on that already. And then the last one again is about the collaboration with all the other research programs at NITheCS. So this is one of the things that obviously will be as a result is African education. So we're building capacity in our departments, in our country, and it's different to the rest of the world. So what we've seen through our NITheCS group is that our complications in our universities are different to international. The way our universities are structured, everything is different. So we need to train for what we are involved at. So at the heart of this focus area, besides the statistics, machine learning, AI, data science, which is our core, is human capacity and research capacity building, which is ultimately what you want from a research program. Okay, and I'm just going to repeat it again. We, number one, want to bring in more HDIs in a more formal manner. So we already have those connections, but we would obviously like to bring them in a more formal manner. We would like to, so my group, NITheCS, is planning a workshop in January. We've done a few workshops in the past, but we'd like to do another one in January. And one of the focuses will be really to find out more about what the HDIs need in terms of capacity building. So it's our theoretical advancement, our academic sustainability, and number three, our community collaboration. Lots of words there. That's if you can read fast and want to read some more, but that's the story there. Right, and then in a picture form, so that you don't have to read all the words. Machine learning, advanced analytics, research community. So the nice thing about stats and computer science is we have various names. Okay, so you'll see here we call it advanced analytics, but I could also be a statistician, I can also be a quantitative analyst. I'm actually a mathematician, so it's a bit weird. Machine learning, AI, data science, they all have these statistics, mathematics, computer science foundation. That's really important. Right, and this is our 4 theoretical work packages. Obviously a bit disjoint, but ultimately contributing to the same goal. And then, of course, we'd like to have another layer on the outside for all the NITheCS groups. And that is my last slide.
Yeah, thank you. Yeah, thank you very much, Ina. Thank you very much for very nice presentation. Next in line is our quantum technology research program, which will be represented by Professor Ilya Sinaisky. Ilya, let's do the swap of microphones. Thank you, Ilya. It was very nice. Thank you. Ilya, over to you. Lost one business class. Sorry?
You go to this.
Of course, right.
Yeah, I should.
In the theater, kind of thing. It was the easiest logistical solution. Otherwise, it would have been dinner here and there too much.
People there.
Okay, good. Good afternoon, everyone. My name is NITheCS, and I will talk about research focus area on the quantum technologies, or kind of the full title, how we'd like to call ourselves, is Quantum Technologies for Sustainable Development. And the PIs on this research focus area of NITheCS is Dr. Sajid Hegg from UCT, Professor Thomas Conrad, who is in the audience, Professor Jeff Morgan from UCT, who is our coordinator, but who could not be here with us today, and myself. Okay? So this is just, you know, for those people who are not with us today. Yes, and Jeff is a coordinator, and I'm a deputy coordinator, and that's why I'm presenting this little presentation. So we also have several other participants. Dr. Kemp from UJ, Professor Kruger from UP, Francesco from here, and Anban Pillay from UKZN, Steph Rue, Dr. Van Zel from UCT, Professor Weltman from UCT, and Ayanda Zungu from NYU, and hopefully soon will be Dr. Zungu. Okay, so we have four main themes, or kind of the four main directions, which we can organize in a little square. So we can see on them that, you know, the two of them are dealing more or less or quasi directly to the technologies, which are called quantum batteries and essentially quantum communication. And there is another direction which is dealing with tools and development of the tools to analyze to this kind of possible application. And one is a generic quantum information tools and application of this. And another one is a little bit more specific, which is dealing with the quantum computing and application of the quantum computing, and the rather specific application of quantum computing, which is called quantum simulation. And in case if some of you are wondering what are the quantum batteries, it's essentially as simple as it sounds. It's batteries which are just driven, or kind of the energy storage systems which are driven on the quantum principles, and due to that, you can get supposedly certain advantages. Yes, the theme which is dealing with the quantum communication, and quantum communication, in case, again, some of you are not familiar with, quantum communication is the way of doing communication which is not rely on mathematical complexity of the algorithms, which is essentially a form of belief, or kind of belief which have a very strong mathematical grounds, but relies on the laws of nature, which, as far as we know, works, as far as we can see. If they don't work, we will need to have another version of the quantum communications. And that theme is dealing with extension of that aspect. So another theme is dealing with the generic quantum information tools. So kind of like as in computer science, there is a classical information theory. Over the probably last 20 years, we see the strong development of the quantum information theory, which generalized classical information theory. And those tools could be applied, and they are applied within this theme, not only, for example, to analysis of the structures, which could be the candidates for the quantum batteries, but also essentially everything up to the earlier universe evolution, as you will see just now. And the quantum simulation and quantum computation is just dealing with what can we do with the devices which are called quantum computers, which exist currently, which are called NISQ devices, or not noisy intermediate scale devices, or what could be done also with the quantum computers of the future, which are called universal fault tolerant quantum computers, which don't exist, but hopefully they will exist on some stage. Okay? And the vision of how the NITheCS is fitting into the development of all of this, that the NITheCS is providing a support towards the first stage of the development. So kind of like on the level of the ideas, for example, in the case of the quantum batteries, or with for the development of some extended ideas for the quantum communications, NITheCS will provide the way how kind of the basic ideas could be developed, and how the kind of the basic, not yet prototypes, but basic ideas, what could be done. And afterwards, other instruments, for example, in South Africa, there is a quantum technology initiative, will be used to build the prototypes. And afterwards, those prototypes, for example, in quantum communication, so in quantum batteries, that could be, you know, afterwards, it could be commercialized if successful. Okay. So What are our program goals? We have several of our program goals. Some of those sounds a little bit serious, but I think after the talk of the Will Horowitz, nothing could be as pretentious as his part of the story. So from this point of view, you know, revolutionized energy storage doesn't sound too bad. Sounds very realistic compared to the unified theory of everything. Okay. And yeah, so revolutionize energy storage, so design and simulate quantum batteries, develop and extend existing quantum communication protocols. So because in the current quantum communication systems, essentially you use for the 1 qubit or bit of information, you use one photon or one particle. And the question is, can we use extra degrees of freedom of the particle to transfer more or more efficient information within the quantum communication channels? So this is kind of practical part of the story, and a little bit more theoretical part of the story is generic advances in the quantum information theory in theoretical physics, so that, you know, these tools could be developed. And basically in these contents, it's a tools related to the objects which are called circuit and the Kirov complexity, and how this could be applied to the many-body system, to the batteries and many other things. Explore various approaches to the quantum computing, because, you know, again, the devices which exist now is only one type of the quantum computers, but they could be, and there is an argument in the community that there could be other types of the ways of doing computations which can give you an advantage. So that's one of the other goals which we are looking for. And also, in more precise terms, kind of the application of the quantum computers and of the current existing and the future to do what is called the simulation, quantum simulation of open quantum systems, which real quantum systems, all quantum systems are realistic, or kind of all the real system are open, and developing the algorithm for these kind of devices. And of course, yes, training the new generation of PhD and master students. Okay. So some of our latest achievements, so in the front of the quantum batteries, there was recently reported that using some special classes of the quantum battery system, which is called SYK systems or such a P-type system, you can get a speed up in the charging, because as in classical case, with the quantum case, you have the same problem. You want to be charged fast and discharged slow, and this is not so easy. As usually, so there are some graph theoretical approaches we're developing to describe the spreads of complexity and so on and so forth. And as I mentioned, you know, these approaches of the complexity, using the complexity theory and the Pareto growth, they applied not only to these quantum batteries, but also to the evolution of the early universe in cosmology, many-body dynamics, and so on and so forth. So also recently, what was developed a way to teleport multiple degrees of freedom of the quantum system, which could be used for the quantum communication. And we reported the development of some NISQ algorithm for the quantum simulation of the quantum systems, and some development and the benchmarking of the quantum machine learning algorithms. And of course, it's all coming within the huge kind of like with the multi-authored papers, collaboration within the local and international partners, and so on. But, you know, I assume that this is a typical story for all sorts of research in the theoretical physics. And this slide is also from the same story as, you know, as it's well known, theoretical physicists are people who convert coffee into the papers, and, you know, that one can continue with these things for a very long time. Okay, so what do we plan to do the way forward? So on the front of the quantum batteries, we plan to develop and keep building the kind of new approaches to describe them, or kind of to build more stable architectures, and explore some recent and very interesting effect, like a Mpemba effect, for example, to extend the Kirov complexity for the open quantum systems, and develop things like that, you know, to use the developed quantum teleportation scheme to adopt it for the quantum communication purposes, and develop new quantum computing and quantum machine learning algorithms, and of course, you know, keep training students for the South Africa. And so how much time do I have, Francesco? Yeah, so I can just quickly show some slides. So this is to the teleportation project, which is led by Prof. Conrad. And if you have some more precise questions, he is here. But the basic idea is very simple, so that, in order to do teleportation, so first, what they're reporting, they learn how to teleport an arbitrary coherent state. So a coherent state which could be created in an arbitrary mode. And if you can do that, afterwards you can take the multiple coherent states, project it on each pixel of the image, and teleport that image kind of like in one go. So in the corresponding references here, and again, this is a typical teleportation scheme, or kind of the variation on the teleportation scheme, but which can do it for the multiple modes simultaneously, which have some certain, informational advantages. Okay, so, and because I'm speaking, so I can spend a little bit more time on project which I led to. So kind of like, for example, there is an example what we have done on the real quantum computers, which exist now, which are not perfect, but we don't execute a very large circuits. And what we were studying here, we were studying some certain transitions in the geometry of the quantum states or in geometry of the quantum channels of open quantum systems. But, kind of the details are not important, but the details are that, essentially it works for the small enough circuits. Modern quantum computers can produce some meaningful results, which is already a good advantage for those devices. For example, in some other approach, what we have done, we have studied the characteristic, because how one should see the modern quantum computers. One should see them as an experimental devices. This is not a computational device yet. But I'm sure that we're going to hear more details, tomorrow, what will be in the future of the quantum computing. But kind of modernly existing quantum computer, it's an experimental setup, and one should treat it as an experimental setup and try to kind of to see what information you can get it. And for example, in this little project, what we have done together with the students, we have extracted the characteristics of the quantum computer as experimental or as an open device. And in that case, what you can do, if you manage to do it successfully, and we managed to do it successfully, but on the next step, one need to make sure that you can design a so-called noise-resistant gate, so how to use this experimental setup in the best possible way. But this research is on the way. Yes, of course, I'm engaged in the traditional quantum algorithm development, and this is just two examples of, when the one student developed, multi-class classifier, and another student have developed a very interesting hierarchical approach to the neural architecture search for the certain class of the quantum machine learning algorithms. And this approach is very promising because now it's applied to the many-body dynamics. Yeah, so we also do different forms of quantum algorithm benchmarking to see how can they be useful or cannot they be useful on some graph theory problems, and and we can also do also play not with quantum machine learning, but play with the classical machine learning for the quantum purposes to find the best circuits to solve certain classes of problems. So, and if you have more questions, or if you want to collaborate and talk to us, please share details.
Yeah. Thank you very much, Ilya. Thank you very much. So let's move to the next focus area, which is our mathematical structures focus area. And Professor Zurab NITheCS is on the way. Zurab, please. Ilya, thank you very much. Please check if he can.
Good afternoon, everyone.
He will give it online.
My presentation today will be more human-centered. I will tell you about some of the key role players in the focus area and also what they do. And then I will conclude with a broader aims and goals and ambitions of the focus area. So we have a few lead researchers. Initially, the proposals that came through to NITheCS for a focus area, as we all know, were grouped. And from the grouping, we selected some of the members of that group to become lead researchers. These were those who had a number of people working in their research groups. But then the other founders of the focus area are still important role players. We call them core researchers. Amorto Goswami is our scientific chair. I will explain what that means a bit later. We have a structure for decision making in the focus area. And some highlights from his bio: he recently received a C2 rating, which was quite an achievement because originally he was an applied mathematician and he moved to pure mathematics, and his rating is for his work in pure mathematics. So it's actually based on just a couple of years of research, and so it's a great achievement that he was able to get C2 rating. And you can see that he wrote 52 papers since 2008. The project that he leads in the focus area is called Analyzing Ideals. Ideals play an important role in number theory. They were first introduced by Richard Dedekind, maybe even before that, at the end of 19th century. Then Emmy Noether made them even more popular. And in fact, Emmy Noether's work on ideals eventually led to a lot of developments in abstract algebra in 20th century. It was quite an influential contribution that she made. So they arise actually across different disciplines of mathematics, and this project is to do kind of bridging of these disciplines. Our next lead researcher on my presentation is Sirine Ratilal. She's based at University of KwaZulu-Natal. She's well known for founding a STEM mentor program, an extremely successful program, which NITheCS also supported a lot, especially initially, but it continues to support. It has now been implemented across the many universities in the country. And she's a project lead for point-free connectivity. Connectivity is another fundamental idea in mathematics that has links with many disciplines, not just inside mathematics. And the kind of the point-free approach is kind of recognizing that the concept of connectivity can exist in realms where you don't necessarily have most fundamental ingredients for your structures, so the points. I see that these slides are not updated. I've been updating them recently. That's strange, but now it's too late, I guess. The update that I added was to list the postdocs that work under each of them. So in fact, there are two postdocs that have worked with Amorto. They are contributing a lot to our focus area. Luca Mesiti here and Elena Caviglia. Their work with Amorto fall directly under the project here. But Luca and Elena also work under a project of Sirine on different topics. And there are two other postdocs that work with Sirine on this project. One of them is based at UWC and the other is based at UKZN. Eric is from Rhodes University. He also has C2 rating. He's editor of Match. Match is mathematical. It's mathematics and computations or computer science and chemistry. It's a journal that brings together the disciplines of chemistry, mathematics, and computation, and he's one of the editors there. It's a Q1 journal, so we're very proud to have him as one of the editors on Match. His project is counting subgraphs. Graphs also are very fundamental mathematical structures, and what he wants to do in his group with his group is to identify a general methods for kind of understanding various parameters of graphs, and they can be applied. Last week, for example, we saw a presentation. There was a meeting that I'll tell you later about. That there was a presentation from a group led by Farania Badza, where they're working on drug discovery by using graph theoretic parameters. It's a very, very exciting development. Do they work with you? So maybe it would be nice to if they did, yeah. So we in this focus area, we're not looking at applications specifically, but I'm just saying that there are surprising applications one might find of graphs in other disciplines as well. Wenqi Kuo, she has C1 rating from University of Witwatersrand. She has a quite remarkable citations to publications ratio. The number of citations divided by number of publications is 11. And she leads a project on Riesz spaces and stochastics. So these are mathematical structures that originate from understanding stochastics, but then they link to various other things in not only within mathematics. It's an interesting topic. There is a group that works with her on this and also related areas. This is myself. I'm one of the editors of Applied Categorical Structures, which is also a Q1 journal. Project that falls under me is a sort of unification of different directions in algebra, topology, and logic, especially from the point of view of fundamentals, by looking at so-called higher structures. So these are structures which show how things are organized when you look at them at a distance. That this approach allows you to identify how to unify things across disciplines. We also have other co-researchers who are not yet lead researchers. As soon as we have more funding for the focus area, we will have projects for each of them as well. Our deputy coordinator, Meggy Afane, is from Sefako Magato Health Sciences University. She has done remarkable work. I mean, she's a mathematician, she very actively published, but she has done remarkable work in terms of attracting students. She joined that HDI university a few years ago, and the postgraduate student numbers have, I think, multiplied by 5 or something. It's really remarkable what she does. And we look forward to actually engaging with these postgraduate students from that university. Setuti Moshoko is from China University of Technology. He's actually former supervisor of Meggy. Brink van der Merwe is from Stellenbosch University. He's working in the overlap of algebra and computer science, very exciting projects that he's working on as well. And Partha Pratim Ghosh is from University of South Africa. This diagram shows the kind of management structure of the focus area. So the overall coordinator kind of is the one that makes decisions, as myself, but I cannot make any decision unless it's approved by the scientific chair. And then even if it's approved, we still want the input of all the core researchers so they can influence these decisions as well. And then sort of lead researchers, when they want to do something, they talk to me to identify what decisions they need for executing their projects. And then the deputy coordinator's role is to provide input from all other associates that are linked to the focus area that are not necessarily lead researchers. Do I have... Oh, fantastic. So quality matters. In South Africa, it's very easy to publish in poor quality journals because universities reward us with the number of publications. So these are the list of journals which in which at least one of the lead researchers has published at least 2 papers. And you see that the list, I mean, some of you might recognize some of these journals are very high quality journals. For instance, Advances in Mathematics is probably one of the top worldwide journal in pure mathematics. They don't publish in applied mathematics, it's just for pure mathematics. And then many other journals are here. So we're very happy to have this long list of high quality journals in which we are able to publish. But also engagement matters. We are very keen on networking workshops for identifying new connections between disciplines. We are also very keen on building skill-building games, especially Elena and Luca are professionals at that, and the idea is to contribute something kind of outside of the usual reach of academia. The theater is there. Then we also organize every now and then exploration activities and research activities for school learners and undergraduate students. This specific photo is from an event last week where many of the members of our focus area participated. You can see here Maggie. This is Maggie. This is Situti. This is the president of Southern African Mathematical Science Association, and this is the president of the London Mathematical Society. In fact, the meeting was between the 3 societies, myself representing South African Mathematical Society, and we identified a few points of partnership across Southern Africa and the UK. One of the nice surprises for us was that the LMS delegation included Giacomo, who is right here. He is a category theorist from UK that works in a very strong group. He himself is a very strong mathematician in UK, and he will be spending 1 week with us after this meeting. Something that's coming up. Well, this is going to be a living kind of document or a book that will report on everything we do, what we do, how we do things, and all of that. We will soon share this with the community. And this one is a workshop taking place next week. As you can see, it's titled Pan-Disciplinary Research on Mathematical Structures. And this is really what we're trying to build in our focus area. So the idea is to, because traditionally research in mathematics is kind of done in silos. So you follow the principles of a particular discipline, and you're then confined with the tastes and the traditions in that discipline, which makes you kind of very separate from other disciplines. So what we want to do as a direction for our focus area is to erase those borders and to rather focus on mathematical structures of particular kind and then explore it across the disciplines, whether it's applied or pure, but the methodology, of course, should be mathematical. This is kind of what underpins the focus area, but then it doesn't have to be confined within traditional mathematical disciplines. So what will happen next week is that Maggie will visit us with her around 10 bring you on board with what we're doing and integrate your work with what we're doing. And now this is about the focus area. In terms of collaborating with other focus areas, we have 2 grand proposals. The first one I already kind of checked with Inger. She was happy with that. So a pan-disciplinary conference series on reasoning that's driven by mathematicians and statisticians. Mathematical reasoning is very precise, but very isolated from the real world, because there's nothing very precise in the real world. And in the real world, everything is based on statistical reasoning. So reasoning is really the thing that unifies mathematics and statistics. It will be nice to have a conference series that might have impact on education as well, because reasoning is one of the important pillars for education, which has really not been embedded as it should in an education system. But of course, AI and the industry also needs this concept. And another initiative would be to have a mathematical structure of the universe seminar series, something that Ilya and I have been contemplating on for a while. I think theoretical physics has developed a lot since Einstein. So has abstract mathematics, and they don't talk to each other so much anymore. And I think it'll be good if they do. Maybe we can solve the problems that Will aims to solve in his focus area. So that's all from my side.
Thank you for using the words that I usually use.
Yes, of course, these words are
they're diffusing. Thank you very much. Thank you very much. Okay, last but not least, let's see if Pedro is online. He's not online. Okay, then maybe we will do it another time. Then we'll have a longer lunch break. Yeah, I think we shouldn't risk to wait here 15 minutes for him to appear. Anyway, thank you very much to all of you for the nice presentations. I hope we were able to give you an impression of the research areas of NITheCS. The climate change Earth system modeling research program we will present another time. I'm not sure what went wrong there, but that's also a very important one, because we don't have our own Southern African climate change model. Yeah, so that's what this research group wants to achieve. Yeah, with the help of everybody. Yeah, so thank you very much again. There should be, according to plan, a finger lunch served somewhere outside. Yeah, I'm sure you will find it. This place is not so big. Yeah, and I would like to thank also the online participants for following us the whole morning. And we will meet again here for the stakeholder meeting at 2 p.m. If you're not a stakeholder, I mean, everybody is a stakeholder, but everybody is welcome to attend as well, of course. Thank you very much. See you later.